So we're going to develop the idea of what's called the change of base property. Like I said, you don't need to write this down right now, but just give you the idea of how it works. We're going to look for a pattern in what we're doing here. And once we get the pattern, we can look at the property that we have written down for change of base and see how it works. So very beginning of talking about logarithms, I said, okay, you can try to calculate this, but it's not an even power that works out to give you 50 from a base of 2. You can approximate it. How would you approximate it? Because 2 to the 5th power is 32 and 2 to the 6th power is 64. This is somewhere in between. We guessed it at about 4.6, and we can verify today that that is in fact true. So we can, I want to show you how you can use your calculator to do logarithms today. Up to now, the work we have done with logs has not been on the calculator. The calculator will only do 2 bases. What are the 2 bases the calculator will do? 10 and E. Some students have a calculator that will do any base. One of my first period students was showing me her calculator. So some of the newer calculators will do any base, but most calculators will only do 10 or E. And the reason is because you can easily change any logarithm to be in terms of one of those 2 bases. And I'll show you how to do that today. The first thing we want to do is think about this as an exponential equation instead of logarithmic. So how would we write this in its exponential form? What's the base? To the power equals 50. So that's how we're thinking about it to try to estimate what that log would be. What I want you to do is we want to solve this for X. And we're going to do that using logarithms. One of the things that we can do to both sides of an equation is take the log with any base that we want. So what I'm going to do is take the log base 10 of both sides of this equation. When I do that, I get this log base 10 of 2 to the X power equals log base 10 of 50. Log base 10 of 50 is something my calculator will figure out for me. On the other side of this equation, I have this log with an exponent here. When we have log of something to a power, we have a property that allows us to do something with that power. What is it? It's multiplying the logarithm by that exponent. So the power property of logarithms allows us to say that that is the same thing as X times log base 10 of 2. And that equals log base 10 of 50. Log base 10 of 2 is a number. Doesn't look like a number, but it's a number that your calculator will figure out. So what we have here is a really simple equation. X times a number equals another number. How do we solve that? To get the X by itself. Divide by log base 10 of 2. And so that is something that your calculator will do for you. You can say X is equal to log base 10 of 50 divided by log base 10 of 2. And you can calculate that. Remember we said this is about 4.6. So grab your calculator and see if you can get that answer on there. If you need to borrow a calculator, I'll message you all.
Yeah, actually,
if you're trying to use your cell phone to calculate logarithms, some cell phones you need to type in the number first and then hit the log button. So if you're trying to do that with your cell phone calculator, try to make sure that you see how that works. Did you get 4.6?
I got 5.6.
I'm sorry, 5.6 because it's between 5 and 6. You're right. So X is approximately equal to 5.6 what? 644, I think is what it was. Generally, I want 3 digits after a decimal on logarithms. 3 digits after the decimal. So what we're saying is that this expression log base 2 of 50 has the same value as log base 10 of 50 divided by log base 10 of 2. Does that make sense? Was there anything special about the fact that we use log base 10? Could we have done the same thing with a different base? Like, for example, natural log. What if I had done natural log of both sides? Well, right here, then it would say natural log, and we would have divided both sides by natural log of 2. So in the end, the calculation would have said natural log of 50 divided by natural log of 2. Type that into your calculator, see what you get. What do you think you're going to get? It doesn't matter what base you use, the log of the 50 and the log of the 2 are going to be proportional. They're going to be the same answer. So you could have done this with log base 8 or log base 5. It just wouldn't be very helpful because the calculator wouldn't do that for us. The change of base property allows us to change any base that we have into something that the calculator will do for us. Does that make sense? So if you see this log base 5 of 89, can we do the same process to think about that? We're going to call it X, and we're going to write it in its exponential form. What's its exponential form? And we can, let's do natural log on this one. We're going to take the natural log of both sides. So that's going to look like natural log of 5 to the X power equals natural log of 89. Tell me what I can do with that. Can't divide yet until we've used the property that moves the X. We've got to be real careful not to skip steps. If you skip steps, your work is going to get confused. So it's going to be X times natural log of 5 equals natural log of 89. And so we can now divide both sides and we get X equals natural log of 89 divided by natural log of 5. Before you calculate it, what should this be between? Between 2 and 3? Closer to, maybe closer to 3. Okay. So calculate that, see what you get.
760.
So it seems to fit where we thought it would. Log base 5 of 89 is equal to natural log, which is log base E, of 89 divided by natural log, which is log base E of 5. So with that in mind, can you do this without doing all the work? Log base 7 of 7,000. What's that answer going to be without going through all that work? You want to use natural log or you want to use log base 10? Log base 10 of what? Log base 2 of 50 is the same thing as log base 10 of 50 divided by log base 10 of 2. Log base 7 of 7,000 is going to be the same thing as log base 10 of 7,000 divided by, exactly. Does that make sense? And that would be the same thing as natural log of 7,000, if you prefer to do that route, divided by natural log of 7. Both of those things should give you the same thing. This is called the change of base property. At the bottom of your notes on properties from a while back, I'm scrolling way back, we have change of base property. It's written right here. It says log base B of X equals log base C of X divided by log base C of B. Let's think about what we started out with here. We had log base 2 of 50 equals log base 10 of 50 divided by log base 10 of 2. In that example, what corresponds to B? The 2. What corresponds to the X? And what corresponds to the C? The 10. So what this is saying is I can, if I have a base that my calculator doesn't recognize, I can change it to base 10 or to base E by using this property. If I have log base 3 of 81, I don't need the change of base property to do that, do I? What's the answer to that? What is it? The answer should be 4, because 4 is the exponent we put with 3 to get 81. But let's do it with the change of base property and verify that it gives us the answer we want. We can say that's the same thing as the natural log, which is log base e, of 81 divided by what? If we do that calculation, the answer should be equal to 4. And it should be exactly 4 unless you're doing some rounding on your calculator. Do you get that answer? So we're verifying that if this property actually works for a problem that we already know how to do.
That works.
Does that make sense? So do we understand the change of base property? If I give you on a test, evaluate something like log base 7 of 250, you can do that with the change of base property. Real simple and easy. So what I want us to do now is use that change of base property along with some other things that we know to solve exponential equations. So can you find this page in your notes? Solving exponential equations. We can do a couple of examples. Don't overlook the problem solving process at the beginning of the notes. This is your key. When I see an exponential equation, I first recognize it as such because it has a variable exponent. And the first thing I want to do is isolate the exponential part. We'll talk about how to do that. The next thing I want to do is take the log of both sides with a base that's already in the problem. And then we'll have to use the change of base property and we'll solve the resulting equation. So we'll go through those steps as we look at each of these problems. The first thing we want to do in each problem is isolate the exponential part. We want our equation to look like something exponential equals a number. That's just a number there on the right. So in that first equation that we see as the example, put a box around the exponential part and ask yourself what's outside it on the left side.
What's the exponent?
It is x plus 4. What's outside the box on the left-hand side of the equation? And it's been added. So what do we need to do first in this equation? So we're going to subtract 0.8 from both sides. On the left, we end up with 4.2 to the power x plus 4. And on the right, we end up with 4.9. Why do we subtract 0.8? To get rid of it, to isolate, to cancel. Because it's the inverse operation of what we see there. Does that make sense? We solve equations by doing inverses. We solve a multiplication equation by division. We solve an addition equation by subtraction. This is now an exponential equation. I have the exponential part isolated. I need to solve by an inverse. What's the inverse of exponential expression with base 4.2? It's a tough question because you're not used to it. But I've been telling you all unit long, I want you to think about logs and exponentials as being inverses in the same way that you think of multiplication and division as being inverses. In other words, when you see multiplication in an equation, you solve it by division. When you see exponential in an equation, you solve it by doing a logarithm to both sides. So logarithm with base that's already in the problem. What's the base that's already in the problem? 4.2. So what we're going to write, and let me just say this before we get too far into it. You need to be writing every problem right now. You need to be writing it with very neat handwriting. You need to be writing it very carefully. Where's your base? Where's your exponent? Because there's going to be a lot of layers on this stuff. And if you don't write it neatly, you will not be able to figure out how to follow your own work. You need to follow the procedure of how to write this and build the habit. Even if you can do some of it in your head, you need to build the habit in the easier problems of how to write the work out neatly so that in the harder problems, you've got a process to do that. So we're going to write log base 4.2 of 4.2 to the power x plus 4. You see how my base is really small and my exponent is small? Kind of over exaggerate where everything goes and what it's supposed to look like. And on the other side, we're going to have log base 4.2 of 4.9. Now let's think about what we can do with what we have here. What do we notice on the left-hand side? Why would we have done the log of that exponential thing? Remember what we did earlier? Inverse properties of logs. This says, what's the exponent that I put with 4.2 to get the exponent to be, I'm sorry, what's the exponent that I put with 4.2 to get the answer to be 4.2 to the power x minus 4? The exponent is this. It's the exponent we already see there. Remember, log base b of b to the x power is equal to x. That's your inverse property. If the bases match, then the only thing that's left over is the exponent. So this thing right here, this thing right here is inverse. And that means that the answer for the left-hand side is x plus 4, which should be the case, because when we do inverse operations in an equation, we do it to make things easier. Now the left-hand side looks a lot easier. Does that make sense? Let me tell you what we don't do. We don't divide both sides by 4.2. We have an exponent, and division is not the inverse of exponent. What do we do on the right-hand side of this equation? We can calculate that thing. We just learned how to calculate that thing, didn't we? So we're going to use our change of base theorem, and we can say log. I would strongly recommend, even though you don't have to write the 10 there, writing the 10 there, because otherwise it gets confusing. Log base 10 of 4.9 divided by, and that's something your calculator will figure out. What did you get when you calculated it? So we can calculate that, and now it's an easy equation to finish. So in the process at the top, it says now solve the resulting equation. Hey, that's easy. Subtract 4 from both sides, and we get x equals negative 2.893. Question, Jet? You're just processing it.
So when you have that, you do log of 4.2, and then on that one, they cancel out.
Uh-huh.
And then when you do it the other side, you just gotta change it to 10 and then change the 4.2.
Yeah, exactly. So when you're choosing how to do the log of both sides, you choose to use the base that's already in the problem, because it will cancel out what's on the left. And then you have to use change of base to make it work on the right. So we'll do another problem kind of similar to it, just to make sure we've got the process. So similar exponential equation. Again, how do we recognize it as exponential? Variable is in the exponent. When we see a variable in the exponent, we know that this is an exponential equation, and somewhere in the problem solving process, we will use a logarithm. We will use a logarithm with base 1. Do not start by, yes, base 4. Do not start by multiplying 2 times 4 and saying that's 8 to the power 3x. Why do we not multiply the 2 by the 4? The reason we can't do that multiplication is the 3x exponent applies only to the 4, not to the 2. So instead of that, we put a box around the part the exponent applies to, and we get rid of the rest. We get rid of the 2 by division, and that's easy division. We get 4 to the power 3x equals 31. Now it is isolated into its simple exponential form. Exponential expression equals a number. So what are we going to do to both sides at this point? Log with what base? So I'm going to write log base 4 of 4 to the power 3x. Notice how you're going to see a lot of, there's a base, there's a regular number, and there's an exponent. And if you don't write that neatly, your work is going to get real confused. And then we have equals, we do log base 4 to the other side as well, of 31. What happens with what we have on the left-hand side? So the exponent is 3x. That's all that remains on the left-hand side. On the right-hand side, it's just a number. How do we calculate that number? This time, let's use natural log just because we want to recognize we can use either. So we will write, or actually, yeah, we'll use natural log and we'll go note to self, change of base. And we'll write natural log, which is log base E, of 31 divided by natural log, which is log base E of 4. So you get 3x is equal to what? So we'll divide both sides by 3 and we'll get 0.826 is what it was. Can you check that answer? Plug it in, multiply it by 3, do 4 to that power, get that answer times 2. You've approximated, so it won't be exactly 62, but it ought to be real close. Does that make sense? One more quick example. I want you to do one that has an E in it. So let's look at this one. Still an exponential equation, similar format, but it's got E and y'all aren't quite as comfortable working with E. So let's get a little more comfortable with that. What's the exponential part? Put that along with its base. So the part that we're going to circle as exponential is the exponent in its base, which is just the E, not the 5. That makes sense? And then what do we do first? So that's easy. And we have E to the power 3x plus 2 equals 150. It's exponential. Questions yet?
So when it's like that, we're just finding it. We don't need to worry about E being like finding the variable.
E is not a variable. So this is some of the stuff that you missed at the beginning of this unit. E is a number. It's when you think about pi, it's an irrational number and you automatically know it's equal to 3.14. E is not a variable. It is an irrational number and it is approximately equal to 2.718. If you need me to work with you a little bit on where that comes from the beginning of this unit, I can do that. But it is a number, not a variable. And when we use natural log, it is saying log with that base, 2.718. So we have the exponential expression isolated, and we need to do the log of both sides with what base? The base that's already in the problem. And so that's E. So we will write natural log, and I'm going to write natural log with base E right there to remind myself every log has a base. And I'm going to put E to the power 3x plus 2. And that's equal to, I do the natural log of the other side. Remember, it's base E of 150. How's that helpful? And natural log of 150 we can calculate. So figure out that decimal number. 5 point what? How do I get the 5.011? You use the natural log button on your calculator, just simply natural log of 150. So we don't need the change of base formula right here. We've used the change of base formula on the other problems because we had it in terms of a base that the calculator wouldn't do. Now we are, because this is a base E problem, it's easy or easier because we can use natural log. So as much as you may say, I don't like E, E makes me uncomfortable, it's actually a little bit easier to solve because you have one less step in the process. So we're going to subtract 2. We get 3x equals 3.011, and we divide both sides by 3, and we get x equals 1.004. Does that make sense? Again, you can check it. You know where the E button is on your calculator, so you can multiply that by 3, add 2, use that as the exponent on E, and then multiply by 5. Questions? How you feel about the process? Good. So what I want to do now is 2 examples of applications that will say, okay, here's the situation that's going to bring up an exponential equation. Can we use this process to solve those 2 equations? The good thing about this is we are, like I said, nearing the end of this unit. And so what we're about to do is going to review a lot of stuff from the very beginning of the unit that we haven't talked about in a little.
So we're gonna bring together, at the beginning of the unit, we talked about exponential functions. And now we're gonna be using an exponential function to solve for a specific value. So this will help you go back and remember some of the stuff you needed to be familiar with from the beginning of the unit as we work through this. Price of a new car is $32,000. Do you remember how to write an exponential function to represent this depreciation? Depreciation means the value is going down. It's going down by 10.5% per year. You remember what format that equation is going to have?
So I'm hearing two different things. I'm hearing a b to the x, and I'm hearing that principal with the 1 plus interest in that complicated formula. The formula you're thinking about is useful for finding interest. Interest is when we're increasing money and it says compounded in a specific way. So that is important to know. It will be covered on your test. But when we're depreciating, it's really an easier formula than that. It simply says our A value means what? The original starting value, which is 32,000. And our B value is that growth rate or decay rate. This is a decay problem. So what kind of number should the B be? Less than 1. What is the B going to be? Yeah. So it's real tempting to say, oh, it's just 0.105. You know, it's 10.5%, but that's how much it decreases by. What we don't care about how much it decreases by. We care about how much value it retains. So we lose 10% from 100%, 10.5%, which, like Andrew said, is 89.5% or 0.895. So the B number in this function is 0.895. Our X represents time and our Y represents final amount. Before we solve this problem, just think for a minute and use your intuition. Car starts out at $32,000. How long do you think it's going to take to depreciate down to 20,000? About. Anybody want to throw out a guess? Without doing any calculation, just throw out a guess. How many years do you think that's going to take? 2? 4? We'll verify that guess in a minute. But what I'm wanting you to do is kind of use your intuition and say, what kind of number should we get here? Because if we end up with an answer like half a year, would that make sense? More than 3 years. If we end up with an answer like 15 years or bigger, it probably doesn't make sense. Cars depreciate faster than that. So if you're saying 3 years, 2 years, 4 years, that gets you in the right ballpark to think about whether your answer is reasonable. So it's always helpful to say, let me make a guess before I give an answer, and then see if my guess seems to line up with what the actual answer is. So we're going to say that the equation that represents this situation is Y equals 32,000 times 0.895 to the X power. I'm answering the question when, which means I'm solving for time. I want to know when the value will drop below 20,000. Really, I can just answer when will it drop to 20,000, and then anything beyond that time will be less than 20,000. So where am I going to put the 20,000? 20,000 equals 32,000, 0.895 to the X power. This looks harder than what we did earlier because the numbers are more complicated, but it's exactly the same as the equation we just solved. What's the exponential part? So what do we need to do to solve it? Is it subtract or is it divide? So look at the operation that's in the equation. It's multiplication. We do the inverse of that. So it will be division. When you do that division, you get 0.625, I believe. So got an exponential. It's backwards from the equations that I did in the examples. The exponential part is on the other side, but it's the same idea. What do we do to solve that?
On base of 0.875.
Yeah, we're gonna do the log with the base that's already in the equation. Log, write the base really small, and as a subscript, 0.895 of 0.625 equals log with base 0.895 of 0.895 to the x power. And the reason for doing that is what happens here. So the answer is x. On the left-hand side, it's just a calculation, but my calculator won't do that. So what do I need?
Log base 10
Now we can calculate that answer. We guess 2, 3, 4 years. Somebody do the calculation, see if our guess was in the right ballpark. On your calculator on your phone, have you been calculating with the other problems today? Okay, then you probably just typed the wrong number in there somewhere. What did you get? You put okay, wait a minute. I did this backwards. I did it wrong, didn't I? I wrote it backwards when I did the change of base. I wasn't paying attention. What's wrong with what I have written here? This number, and that's my fault. This number goes on top. I was writing it too fast. And this number, the base, goes on the bottom. So sorry about that. That's why we're getting something that doesn't make sense. So it's the 0.625 on top and the 0.895 on the bottom. If we calculate that, that should make more sense.
Yeah, I got a negative 0.2.
This time you did?
I got 4.23. I got 4.237.
Abby, do you have your decimals in the right place? If you're having trouble with the calculation of it, make sure you've got the work written down and I will watch you calculate it. You got it that time. Yeah, you probably just typed in the wrong number. So is that reasonable? Does it fit with what we said? Yeah, 4 years, we were saying 2, 3, 4 years, something like that. So it does seem to fit. Questions on that? Let's do one more example. It's the number that you're doing the log of on the top, the base on the bottom. And I wrote that backwards. That was my fault. Yeah. So if you look back at every other problem, that's the way it works. And if you look at the change of base property, the base part is the one that's always on the bottom. And if you get that backwards, you'll get it wrong every time. So, and your answer won't make sense. If you get an answer that's unreasonable, don't stick with an unreasonable answer. Look at your work and say, what can I change? What might I have done incorrectly? Try to find the mistake. Don't just move forward with a mistake. Here's one more problem. What jumps out at you when you read that?
Continuously using that BERT.
So we have the formula A equals P E to the RT. So this is taking us back again to the beginning of the lesson, beginning of this unit where we were learning about continuously compounded interest. The word continuous compounding is what indicates this formula. In this formula, what will be the value of our P? Which in this case is,
3,500.
and the interest rate, E is just our 2.718. The interest rate here, how am I going to put that into the equation? We're going to type it in with a decimal. I had somebody in the last hour say 1.045425. If you look at your notes carefully, it says don't add the 1. If you do add the 1, your answer is going to be completely unreasonable. So you say, well, what did I do wrong? Try to go back and damage control on that. What can you change? Take off the 1 and you'll see that your answer is reasonable. And then T represents time. And A represents final amount. So we will write the function that represents this situation, which is A equals 3,500 e to the power 0.0425 t. Now let's look at the question. Again, we're answering when. So we're trying to find time, which is our x value in this problem, or a t value. Trying to solve for the exponent. That doesn't give me a number to plug in.
But it says it needs to be, find out what it will be, worth twice the value, so A will be 7,000.
So it says we want the final amount, and it tells us in the problem, double the original value. So it's 2 times 3,500, which is 7,000. Good job. So even though it doesn't give us a number, we read it and we say, oh, we know how to double a number. And we can interpret that to be 7,000 equals 3,500 e to the power 0.045 t. It's exponential. Put a box around the exponential part. What do we do? Before we work through it, you want to give a guess? We got 4.5%. We're trying to double our money. 10 years, 10 or 11 years. Okay. So we've got a ballpark, and do the rest of you think that sounds reasonable? You know, 50 years is going to be probably way too long. 2 years is not going to be nearly long enough. So, you know, 10 years, 12 years, something like that. We'll see what we get. What are we going to do first? And what's interesting about what we get when we do that? How did we get 7,000 to begin with? Yeah, so we doubled the value. We end up with just 2 right here. Equals e to the power 0.0425 t. This is the point where you're taking a test and you're like, oh, wait a minute, I'm stumped. I don't remember what to do with that, right? Because this is the new thing. This is the thing that you haven't seen before. So this is where I've been trying to train you to say exponential is the inverse of logarithm. So to solve something exponential, I need to do logarithm to both sides. And that's what you need to learn here. So that when you see that on a test, you don't get stumped at this point. What do we do to both sides here? Natural log, because our base that's already in the problem is e. So natural log of 2 equals natural log of e to the power 0.0425 t. If you will write little base e next to your natural log, just to remind yourself that it's log base e, and then write the expression e to this power, you will see how that inverse situation works. So what are we left with on that side? And on the other side, this is just a number, and I'm going to just write natural log of 2 because it's easier to write natural log of 2 than to punch that in the calculator and get the decimal number and write it down. So to finish it, what do I need to do? Both sides by 0.0425. So my time is equal to natural log of 2 divided by 0.0425. And you can get an answer there. Turns out to be 16.3 something. Question, Lauren? Okay. So we're dividing, we get our answer 16.3. A couple of you guessed 10 or 11 years. Are we still in a reasonable range? Yeah. Couple of things I want to mention. You're taking a test, you get to the point where you've got this equation written down, and you're like, I can't remember how to solve this. So you can grab your calculator and start doing a bunch of guess and check. You say, well, I think it's 10 years. I'm gonna plug in 10. Nope, it's gotta be longer than that. I'm gonna plug in 12, I'm plugging 15, plug in 16. You can guess and check until you can get it pretty close to accurate. Are you showing me, if you do that you have learned anything about logic?
You're showing me that you've learned something about a compound interest situation, and that's good, but you're not showing me that you understand logarithms. And this part of the unit is, do you understand that logarithms are the inverse of exponents? And that is how we solve an exponential equation. If you are not showing me work using logarithms and you are just simply plugging into your calculator and doing guess and check, are you doing higher level math? I'm testing your ability to do the math that we learned in class, not your ability to go around the math that we've done in class and use things that you could have done before. Does that make sense? Guess and check is good math. It's a good way to work a problem if you can't think of anything else, but it's not a great way. I'm trying to teach you the methods that are more sophisticated mathematical thinking. So if you want credit on your tests, you need to not be just defaulting back to stuff you could have done before. That makes sense? Another thing I want to mention, I see a lot every time I teach logs and I'm looking at homework or progress checks or things like that, I see work that is very obviously copied from Mathway or Photomath. I'm just going to tell you right now, Photomath does some weird things with logs. And I know what those weird things are. And when they show up on assignments, it tells me you're using Photomath. And so I'm going to tell you right now, don't use Photomath. It'll give you the right answer, but your work and your process is going to look like stuff that we have not done in class and stuff that I have not taught you how to do and stuff that really doesn't make sense. It's mathematically accurate, but it doesn't make sense in terms of the problem solving process. So don't use Photomath, don't use Mathway. If you need to check your answers, you can plug your answers back in and check them to see if they're right. But teach yourself the right process instead of trying to go around. Make sense? So you've got about 5 minutes left. I want you to get started on the homework assignment, which is on page 375. I want you to do at least 2 of those problems on your own while you're here in class with me. Don't skip steps, because even if you can skip steps, a few steps here and there to get to the answer, if you skip steps, you're losing part of the problem solving process and you're going to miss things on some of the harder problems. Take a second to get started on that. Let me know if you have questions.
Sure.
What?
What?
Lesson like this, yeah. Anybody else need a book? 275.